So obviously we know that if f prime is positive, that implies that a function is increasing, right? But we can actually get more specific in terms of how we talk about a function and whether it's increasing or decreasing. So first, let's look at these two graphs, and we'll say these are f graphs, not f prime. Okay, so what is similar about these? Let's make a table. Similar. Okay, well, if we look at both of these functions, they're both increasing functions, so we can say that f prime is always positive. It's always positive because the functions are always increasing. Yeah? Okay, what's different about them? And you could probably come up with a decent amount of differences here, but the main difference that pops out to me is that one is getting steeper while one is flattening out. Getting steeper versus flattening. So how can we deal with f prime to specify when like obviously f prime tells us whether a function is increasing or decreasing, but how can we take it further and determine whether a function is getting steeper or flatter? And we're actually going to use a vocab term today which talks about how the function is curved. So in this case, the function is getting steeper and its curve, the curve is, we call this concave up because the curve is up. Whereas here, the function is getting flatter, and we call this concave down. So how can we talk about concavity of a curve in addition to its slope? So here are two f prime graphs now. From x equals 2 on, what is similar about these graphs? Well, so here's x equals 2, and then we're going from there, right? Here's x equals 2, we're going from there. Well, at least in this picture, from 2 until this x-intercept, and from 2 until, well, until the graph cuts off here, f prime is positive. F prime is positive, right? So what's the difference though? Well, one, f prime is increasing, and in one, f prime is decreasing, right? And in this case, we could talk about, well, the slope is positive and also the slope is getting bigger, right? And what is a bigger slope going to look like? Well, it's going to look like a steeper curve, right? So for this one, f of x is getting steeper. Whereas what's happening to the curve here? Well, the slope is approaching, what is the slope approaching? It's approaching a slope of 0, right? And what is the slope of 0? Well, it's a completely flat slope. So in this case, f of x is getting flatter as x gets bigger, okay? So this is our introduction to start to talk about concavity. It's going to have to do with how f prime x is changing. It's not enough to know whether it's positive or negative. We're now going to talk about whether f prime is getting bigger or smaller, okay? So here's a graph of f prime, and we're now going to introduce this idea of f double prime, which is just the derivative of f prime. So if this is the graph of f prime, and f double prime is the slope of this graph, when is f double prime positive or negative? So let's draw this picture and label this. So right here, f double prime positive, and then the next section where f prime is decreasing, we have f double prime is negative, and then we have our last section where f double prime is positive again. Okay? So how does that relate to concavity? So now that we're able to identify where f double prime is positive versus negative, we should think about what does f double prime actually represent. So let's look at some different options here. So we're going to draw a curve where f prime is positive and f double prime is also positive. So f prime being positive would mean the curve is increasing, but f double prime being positive would also mean that f prime is increasing, okay? So we need to draw a function where the curve is getting bigger, it's increasing, but also the curve is getting steeper because f prime is increasing. And that would look something like this. Okay? Now let's draw one where f prime is negative, so the function is decreasing, but f double prime is positive, so that would imply f prime is increasing. So if we're going to draw a curve where f is decreasing but f prime is increasing, this is a little bit counterintuitive. Okay, it's going to look something like this. Okay, because, and you may think, well, but if f prime is increasing, that would mean the function is getting steeper. But no, because right here, let's label this. Right here, the slope is negative, right? And if we picture where this slope would fall on a number line, if this is slope 0, okay, it's going to fall somewhere over here, right? And then what happens to our slope? What happens to our slope as x gets bigger? Well, the slope is moving towards a slope that's flatter. It's closer to 0. And if we think about our number line, then that's going to cause us to go this way, which would imply that f prime is increasing. So when the function is decreasing and getting flatter, that means that f prime is increasing. So then if we go here, we want f prime to be positive and f double prime to be negative. So we want f prime to be decreasing. So that means that the function is getting bigger, but the slope is getting smaller. So if the function is getting bigger, but the slope is getting smaller, the slope is going to have to approach the slope of 0, has to flatten out, right? Now what about here? F prime is negative, so f of x is decreasing, but f double prime is also negative, so f prime is decreasing at the same time. Okay, a function that is decreasing where the slope is also decreasing, again, a little bit counterintuitive because it's going to get steeper. How the curve would look something like this. Because, again, right here, we have a slope of 0, right? So if we look at our number line, here's our slope. And then what happens to our slope as x gets bigger? Well, our slope is becoming a larger negative number, which means we're going this way on the number line, right? If we were to look right here, this is going to be a number, like let's just give it, let's say it's like negative 10, right? Well, negative 10 is over here. So we've gone from 0 to negative 10, which means that f prime has decreased, okay? So let's see what we notice here. Whether or not f prime is positive or negative, if f double prime is positive, then the curve is concave up, right? But whether or not f prime is positive or negative, if f double prime is negative, the curve is concave down. So that's exactly what f double prime tells us. It tells us the concavity, right? F double prime tells us concavity of f. So it tells us how the function is actually curved. So if we go back to this picture, then we would say that at first the function is concave up, and then we can just use, usually we use CU to abbreviate, CD, concave down, and then CU. So here's a graph of f prime, and now another vocabulary word is a point of inflection, and that's where the concavity of the curve changes. So we have a point of inflection right here and right here in this graph. And this one, again, this is going to be where f double prime switches signs, which is always going to happen at a maximum or a minimum of f prime. Because right here, f double prime, what does it do? It goes from negative to positive. So we're going from concave down to concave up, and that is a point of inflection when that happens at the minimum. Okay, and then we have right here, f double prime, the slope of f, is going positive to negative, so that's CU to CD, concave up to concave down. All right, and how would this look in a graph of f? Okay, if we want to draw an example of a point of inflection, is it would look something like this. Okay, right here would be a POI because we're going from concave down to concave up. Okay, it could also look something like a shoulder, right? A shoulder could also be a POI because we're going from concave down to concave up. Okay, it could also be concave up to concave down. It could be the reverse, like that, right? Okay, there is a POI, point of inflection. So let's do a simple example, x squared. F of x equals x squared. F prime x equals 2x, and f double prime x equals just positive 2. So f double prime is never changing. It's always just positive 2, which implies that the curve is always concave up. Okay, What about our slope? Well, our slope is going to be negative when x is negative and positive when x is positive. So the function is going to start by decreasing and then it's going to increase, but it's always going to be concave up. And all of this probably seems obvious to you because you know how x squared looks. It looks like this. Oh my gosh, one of these days I'll get it to actually hit there we go, the origin. Okay, so the function decreases and then it increases, but it's always concave up because f double prime is always positive. Okay, one more example. We'll do sine x. Okay, so this one's going to be a little bit more tricky. F prime x equals cosine x. F double prime x equals, what's the derivative of cosine x? That was negative sine x. So, and we're going from 0 to 4 pi, so now it's a matter of just remembering things about cosine and sine. So let's draw our unit circle. Okay, cosine on our unit circle, remember, is the x value. So remember that cosine is positive in these two quadrants and negative in those two quadrants, right? So we can say the function, if we just go around our circle, is increasing, decreasing, decreasing, increasing. Okay, it increases, it decreases, it keeps decreasing, and then it starts increasing. And we know this about sine, because if we were to look at a graph of sine, it starts at 0, it goes up to its max at pi over 2, and then it decreases, and then it keeps decreasing, and then it increases again to go back to the x-intercept, the x-axis, okay? So it increases until pi over 2, it decreases, and then it keeps decreasing all the way until 3 pi over 2, and then it starts increasing, okay? We can see the concavity now, so let's actually pin down how this relates to f double prime. So normal good old sine x is positive in the top two quadrants and negative in the bottom two. But because this is negative sine x, that's going to be flipped. So we have negative, negative, positive, positive. So from 0 until pi, this function is concave down. And then from pi until 2 pi, it's concave up. And we can see that on the graph. It's concave down and then it's concave up, right? So increases, decreases, decreases, increases, decreases, decreases, increases, concave down, concave up. And technically this problem says to go from 0 to 4 pi, but we know that this is just going to repeat again. It's just going to do one more of these cycles where it, again, cycles through increasing, then decreasing, then increasing, and then cycles through being concave down and then concave up. So that is f double prime and what it represents graphically. And whenever you have whenever you hear a question about concavity, that means you have to look at the second derivative, f double prime.